Hello, in this video I'll be going over the general periodic table trends in order to recall a bit of information from the first unit of AP Chemistry in order for us to kind of mold and adjust our way into getting a good mindset for the AP Chemistry exam. First and foremost, I'd like to begin with electronegativity. And essentially, electronegativity is an atom's tendency to attract electrons to itself. Now, electronegativity is characterized / defined by the symbol chi, which is a Greek letter that looks like the letter X. And the general relationship for electronegativity is that when you go from left to right across a period and down to up across a group, your electronegativity will increase. Now, allow me to explain. So when you go from left to right across a period, your proton count will also increase. So lithium has 3 protons, beryllium has 4 protons, boron has 5 protons, carbon has 6, and then so on and so forth. So left to right, you're increasing in your proton count. This means that you have an increased positive charge within your nucleus, and this also will then exhibit a greater nuclear charge within that atom. Because of this greater nuclear charge, the atom will have much greater attractions towards electrons, and these electrostatic forces where electrons are attracted to a positively charged nucleus is known as Coulombic attractions. And from this general direction, your Coulombic attractions will increase. In addition, when you go down to up from a group, your atomic radius will also decrease. Now, when you combine these two factors, a smaller atomic radius plus a greater positively charged nucleus will essentially maximize the rate of attraction and the tendency of an atom to maintain the grasp of such electrons to itself. And just for reference, fluorine has the greatest electronegative charge, which will amount to a value of 3.98. Just something you should keep in the back of your mind. Alright, now the next trend is ionization energy, and this is essentially the opposite as electronegativity, and this is the amount of energy that's required to remove an electron from an atom. Now, although ionization energy and electronegativity are essentially two different opposites, they will both follow the same trend regarding the periodic table. So as you go from left to right across a period and down to up across a group, your ionization energy will increase. Now, the same justification goes for both directions from the periodic table. As you go from left to right, your proton count will increase amongst the atoms, and from down to up, you're decreasing your atomic radius. A greater positively charged nucleus exhibits a greater nuclear charge, which attracts electrons to a greater extent, and this small radius will make the attractions even stronger compared to atoms with large radii or large atomic radii. And in this trend, I would also like to go over multiple ionization energy levels. So it's possible for an atom to undergo multiple stages of ionization energies, and we just mark them with a simple number which represents the number of times an ionization occurred within an atom. So we have ionization energy 1 here and ionization energy 2. And I'll actually use boron as an example. So on the left here, I'll make a diagram which represents boron, just a rough sketch because boron has 5 protons in its neutral state, it'll also have 5 electrons. So this will be boron's rough sketch, and on the right side I'll draw its electron configuration and its electron spin, which I'll cover in a future video. So boron's electron configuration is 1s2, 2s2, and then 2p1. So we'll have 5 electrons which show opposite spin. So when I undergo the first ionization energy, I'll be removing an electron from an atom. That's the definition of it. So my atom will most likely want to get rid of its outermost electron from the outermost shell. So after the first ionization energy, I'll remove that respective electron from that spin. However, when I undergo the second ionization energy, notice how both of my electrons in their respective energy states are joined together. They're both electron pairs because they're both in a group and they have opposite spins. So because they're conjoined in a pair, they don't want to split apart from each other because they're already satisfied with the pair that they already have. They don't want to split away from that. Therefore, the amount of energy that it takes for the second ionization energy to occur will be much greater compared to when I just simply remove this electron, because it's essentially a lone pair in its respective energy state, making it a lot easier to just get rid of as opposed to removing an electron from a pair. So always know that the second ionization energy will always be greater than the first ionization energy because of that relationship. The next one is electron affinity, and this is the energy change that results from adding an electron to an atom, which is represented by kilojoules per mole. In other words, electron affinity is an atom's readiness to accept or to attract an electron to itself. So kind of like electronegativity, which is why we are going to follow the same trend as we did for ionization energy and electronegativity. Left to right across a period and down to up across a group will increase your electron affinity. Now, once again, this is because of the combined factors of having a smaller atomic radius and a greater nuclear charge from your positively charged nucleus, which encourages the attraction of electrons towards such respective elements. Now, note here in red that nonmetals will have greater electron affinities. When we're referring to the nonmetals, we're referring to this chunk of elements right here. These are the alkali metals, group 2 is the alkali earth metals, and 3 to 12 is all your transition metals. So from groups 1 to 12, those are all of your metallic elements. But starting from 13 to group 18, that is when you have your nonmetals. And if you didn't know, the general relationship for the groups and their valence electrons will be that group 1 will have 1 valence electron in its outermost shell. Group 2 will tend to have 2 electrons in its outermost shell. And then 3 gets a little funky, but for the most part, their valence electrons will most likely be 3 electrons. From here, group 13 will be 4 electrons, 14 will be 5 electrons, and then goes all the way up to 8, where you reach the noble gases. So now, it's easier for non-metal atoms to obtain and attract an electron because they're trying to create an octet pair for themselves. An octet pair is basically when an atom has 8 electrons within its valence shell. Because they have more valence electrons compared to the metal elements here, it's going to be easier for them to want to accept an electron in order to try completing that octet pair, which is why that the electron affinities of nonmetals are greater than the electron affinity of just metallic elements. And then finally, the last key periodic trend you should know is your atomic radii. So the atomic radius is just the general size or measurement of an atom. So basically, the more shells that an atom possesses, the larger it is. In other words, if you have more electrons within an atom, then you will have more electron shells, making your atomic radius bigger. And now this is the only trend that differs from all of the other three. So actually, as you go from right to left across a period and up to down across a group, that is when your atomic radius will increase. And for this reason, metals will have larger atomic radii compared to nonmetals, which should make sense. So the atom with the largest atomic radius would be francium because of its electron shells and it's essentially on the opposite side as to these non-metallic elements. So those are some of the basic periodic table trends that you should know and kind of understand in order to apply into questions regarding properties of atoms and elements.